A radar operator stares at a screen that has never lied to him. The sweep line rotates, the sky is clean, and the defense network is ready. In theory, the moment an aircraft enters range, the system should detect it, track it, assign it, and destroy it. That's the air defense kill chain. See, track, target, engage. Stealth was built to break that chain, without magic, without invisibility, without Hollywood. Stealth is engineering that steals time from the defender. And in modern war, time is life. The real question isn't can you see a stealth aircraft? The real question is, when you finally see it, do you still have time to react? Even the public messaging from official programs is blunt. JSFMIL, official Joint Strike Fighter program site, says stealth is not invisibility. It's the ability to elude or greatly complicate an enemy's ability to find and destroy an aircraft. And Lockheed Martin's official F-35 site repeats the same idea. Stealth doesn't make the jet invisible, but it complicates an adversary's ability to find and target it. That's the baseline truth. Stealth buys advantage by compressing the enemy's timeline. So how does it do that? We start with radar, because radar remains the backbone of modern air defense. Radar works by transmitting radio energy and listening for the reflection. The size the radar sees isn't the physical size of the aircraft, it's the strength of the echo. That measurement is called radar cross-section, or RCS. The mission of stealth design is to reduce RCS so the aircraft blends into noise, uncertainty, and delayed detection. Stealth attacks radar in two major ways: shaping and materials. First, shaping. Encyclopedia Britannica explains that stealth aircraft minimize radar returns by controlling surface geometry, limiting openings, and designing shapes that deflect radar energy away from the transmitter. A conventional fighter has features radar loves: vertical tails, pylons, external weapons, round inlets, exposed engine fans, and sharp corners. Those features create strong reflections, clear targets. A stealth aircraft tries to remove or hide those reflections. Surfaces are angled, edges are aligned, and critical components are masked so the strongest reflections do not return to the radar source. That's why stealth aircraft look the way they do. Their shape is not primarily aesthetic, it is survival geometry. Second, materials. Shaping can redirect radar energy, but you cannot redirect everything. So stealth aircraft also use radar-absorbing materials and coatings that reduce reflected energy. Encyclopedia Britannica describes absorbent materials as part of stealth design and also notes the price. Absorbent materials add weight and can reduce range or payload. That's important. Stealth isn't a free upgrade, it's a trade. Now here's the first myth we have to kill. Stealth does not mean undetectable. It means harder to detect, later to detect, and harder to track. The difference matters because detection is not the same as targeting. An air defense system doesn't just need a faint hint that something exists. It needs a stable track, enough confidence to fire, guide, and hit. Stealth aims to keep the enemy stuck in doubt. A weak return, a broken track, an uncertain target. And while the defender hesitates, the attacker moves. But stealth performance is not constant. It depends on angle, distance, altitude, and frequency. That brings us to the second myth. If it's stealthy, radar can't see it. The reality is more complicated, especially across radar bands. Most stealth aircraft are optimized to reduce signatures in the radar bands commonly used for fire control and missile guidance, bands that offer high precision and resolution. But many analysts point out that lower frequency radars can sometimes detect stealth aircraft differently because long wavelengths interact with aircraft shapes in ways that are harder to fully control. That doesn't automatically defeat stealth. Low-frequency systems often lack the precision to guide a missile on their own, but they can provide warning and cueing, telling the defender where to look. In other words, they can help rebuild the kill chain in pieces. And modern defense isn't built around a single radar, it's built around networks. This is where counter-stealth loopholes appear. One serious concept is bistatic or multistatic radar, systems where the transmitter and receiver are separated. A stealth aircraft is shaped mainly to avoid reflecting energy back to the transmitter, but with separated receivers, scattered energy that doesn't return to the transmitter might still be captured elsewhere. That can help detection. It may not yield a clean weapons-grade track by itself, but it can increase warning, improve cueing, and push stealth closer to the enemy's trackable zone. Now, radar isn't the only sensor. Heat matters. That brings us to infrared detection. Stealth is heavily associated with radar, but modern aircraft can also be detected by infrared search and track systems. Encyclopedia Britannica notes that engine exhaust is a major contributor to an aircraft's infrared signature. Stealth designs attempt to reduce and manage that signature through exhaust shaping, shielding hot components, and reducing exposure of the hottest parts. But there is no escaping physics. Jet engines produce heat. In the right conditions, a capable IR sensor can detect aircraft even if radar struggles. Infrared has limits too: weather, atmospheric absorption, background clutter, and difficulty estimating range. But it's a real threat vector and a real part of modern counter-stealth doctrine. Now comes the third myth: stealth aircraft cannot be shot down. History already answered that. The famous case is the F-117 shootdown during the 1999 Kosovo conflict. Wikipedia Stealth Technology Overview summarizes stealth technology as a set of methods to reduce visibility to radar and infrared and other detection methods, not eliminate. That framing matters because it keeps expectations realistic. What happened in Kosovo was stealth failed. It was a reminder that stealth is not invulnerability. Predictability, tactics, route repetition, timing, and defensive adaptation can create opportunity. Low observability reduces risk. It does not erase risk. But there is an even more overlooked vulnerability, one that almost never goes viral because it's not cinematic: maintenance and environment. Stealth depends on surface condition. Panel seams, coatings, and low observable treatments must be preserved. A U.S. Government Accountability Office (GAO) report on the B-2 bomber stated that testing indicated the aircraft was sensitive to extreme climates, water, and humidity, and that exposure to water or moisture could damage some low observable enhancing surfaces. That's not internet rumor. That's a government audit. It means stealth is partly a condition you maintain, not just a feature you own. This feeds into the fourth myth: stealth works the same in all weather. In reality, rain, humidity, salt air, and abrasive environments can degrade coatings and surfaces, which can increase signature until repaired. That's why stealth bombers and fighters often require careful maintenance cycles and controlled facilities. Modern designs have improved coatings and maintainability, but the principle remains: low observables demand discipline. And then there's cost. Encyclopedia Britannica notes that stealth design introduces penalties like weight and maintenance difficulty, and the history of stealth bombers shows how expensive low observable capability can be. Stealth aircraft are strategic assets, but they are not cheap assets. The operational question isn't just can we build it, it's can we sustain it at scale under real-world deployment conditions. So what does stealth actually deliver on the battlefield? Stealth is not a promise of invisibility. It is a promise of advantage. It reduces detection range, delays tracking, and compresses the defender's engagement window. It allows attackers to strike high-value nodes, radars, command centers, launchers, before the defense network can respond effectively. It creates uncertainty and forces the defender to spend time confirming tracks instead of firing confidently. And when stealth is combined with electronic warfare, decoys, standoff weapons, and disciplined emissions control, the defender can be overwhelmed by complexity. But stealth also carries operational limits that matter in real planning. One limit is payload configuration. External weapons and external fuel tanks damage stealth. That is why stealth aircraft often carry weapons internally during penetration missions. That can limit payload compared to non-stealth aircraft loaded with external stores. Yes, many stealth aircraft can carry weapons externally when low observability is less critical, but that is a conscious trade. Accept greater detectability in exchange for more firepower or range. Another limit is emissions. A stealth aircraft can be radar stealthy and still give itself away through active transmissions if it is careless. Modern doctrine emphasizes emissions control and sensor fusion so the platform can see without loudly broadcasting. The goal is to stay quiet, stay low observable, and let the enemy struggle to build a track. Now let's talk about the big misconception that fuels online arguments: stealth is either perfect or useless. That's a false choice. Stealth is neither. It's a sliding advantage. When the aircraft is clean, maintained, flown intelligently, and supported by a wider force package, stealth is devastating. When the aircraft is exposed to harsh environments, operated predictably, or confronted by layered sensors, especially networks that combine different radar bands with infrared search, its advantage can shrink. This is why stealth is still valuable. It forces the defender to spend more resources to see less, and it ease them to act with less confidence. It shifts the balance from the defender's strength, early warning and tracking, to the attacker's strength, surprise, and timing. And the contest continues. Defenders invest in better processing, better networking, more sensors, and smarter fusion. Attackers improve materials, manufacturing, mission planning, and signature management. This is an arms race of observation and deception. So here is the final truth, stated cleanly: stealth doesn't win wars by being unseen. It wins by making the enemy see too late. It's a strategic tool that targets the defender's timeline, not their eyesight. If your definition of stealth is the enemy never knows you were there, you're chasing fantasy. If your definition is the enemy knows when it no longer matters, you're thinking like a military planner. So the next time someone says stealth is a cloak or says stealth is fake, remember what the official program language from JSF Mill and Lockheed Martin, the technical explanations from Encyclopedia Britannica, the historical framing summarized by Wikipedia, and the hard operational realities recorded by the U.S. Government Accountability Office all point toward: stealth is real, but it's not magic. It's physics, engineering, and discipline, designed to steal time from the defender. Next mission, we go on the other side of the fight. Counter-stealth radar networks, passive detection, infrared tracking, how the hunters are evolving to find what was built not to be seen. Subscribe if you want that briefing, because the next air war won't be decided by who flies the loudest jet, but by who controls what the enemy can detect and when.